Hello, my name is Gabrielle Taylor. I'm going to be doing homework 4, part A1. So the problem says, starting from a non-steady state mass balance for a gravity drain tank with an inlet full of Q, we're going to linearize the differential equation and derive an expression for the transfer function relating to H, and H as in height and Q as in flow into the tank. So the first thing that we want to do is we're going to draw our mass balance. We're going to draw the tank. So the tank is a drainage tank. So it has a Q going into this, as in Q. And then coming out of it, it has a minus. And then we have an alpha. This alpha is going to be constant because of the outlet area is going to be constant. So, and then this is going to be multiplied by H times the 1/2. And then this is the liquid is at some height as H. So let's first do our mass balance. So our mass balance is going to be the area times the change in height times the change in divided by the change in temperature time. And then this is going to be multiplied, is going to be equal to Q. So our flow going in minus what's coming out of our tank, which is alpha times our H to the 1/2, right? So next we're going to do this for steady state. So we can't use this right now for a Laplace transform because the H is to the 1/2. So we can't use a Laplace transform for that. So what we're going to do is a linearization for this, and we're going to use the Taylor's expansion series to help us use this for Laplace transform. So the first thing that we want to do is initialize our steady state stuff. So before we get any kind of confused with this, we're going to have our initials for our steady state. And so we know our initials is going to be H bar, and then we're going to have Q bar for these two. So now let's do our equation for it. So it's going to be area times dH dt. It's going to be Q minus, and we're going to pull out our theta, and then it's going to be the square root of H bar plus, then we're going to have 1 over alpha times our H bar, our square root of H bar. And then this is going to be multiplied by H minus H bar. And I'm going to kind of go like that so you can see. Okay, and then this has one more parentheses around. Okay, so then after this we're going to kind of have a derivation of our variables. So we're going to have our Q prime is going to be Q minus Q bar. So this is our current Q minus our Q at our steady state. And then our H prime is going to be our height minus our height bar. So our height minus our height at our steady state. So after this, we're going to do our this equation, but at steady state. So when it's at steady state, we know that the height is not going to be changing, so this is going to be 0, right? So there's no change, so it'll be 0, right? So then you have our Q minus our alpha times the square root of H bar plus, and then we're going to have 1 minus 2 over H bar times H bar minus H bar. So this is at our Q prime. Now what we're wanting to do is when it is at a normal, not at a steady state, and we're going to subtract it by a steady state, we're going to come up with an equation there. So let's do that equation. So that equation is, so we're going to have area times dH dt is going to be equal to, so we have think, oh, this is at Q bar, by the way, because this is at steady state. So this needs to be Q bar. That makes sense. Okay, anyway, Q minus our alpha times our square root of H bar plus our alpha over 2 over H bar times H minus H bar. Okay, and then we're going to subtract this by our steady state. So it's going to be 0. And then this is going to be Q bar minus alpha Q minus Q times the square root of H bar plus minus this. Oh, also, since we took this and we multiplied it out just like here, so this is also going to be negative. So that's important. So in this equation, we are also multiplying out this alpha. So it's going to be negative as well. And that's going to be alpha over 2 H bar. And then we have H bar minus H bar, right? So let's see if we can cancel out anything. And I'm going to put the answer up here for it. So H bar minus H bar. So our height at the steady state minus our height at the steady state is going to be 0. So that whole term is 0. And then we can see here that these are the two of the same terms and we're subtracting them. They're going to cancel out. So now let's see what we have left up here. So we have area over dH dt is going to be equal to our Q, and then we have a subtraction, so minus Q bar. So our Q at the steady state, so our flow at the steady state. So these two terms cancel out, so then we're having this term here. So then minus our alpha. I'm going to pull out the alpha for now. So just like multiply by it, and then we have 2 times our H bar times H minus our H bar. Right? And then some things we can see. Well, when we derive right here, this here is going to be our Q prime. And then this here is going to be our H prime. So let's rewrite this. So the area of dH dt is equal to Q prime minus our alpha plus our 2 over H prime over H bar, and then we have our H prime multiplied by H prime. So the next thing that we want to do after this is now we can use our Laplace transform. So our Laplace transform of dH prime over dHt is going to be equal to Hs, and then we have our Laplace transform of Q prime is going to equal Q, and then our Laplace transform of H prime is going to equal H, capital H. So now we have these, we're going to plug them back into our equation that we have up here. So we have A times HS, and then we're going to do minus, and we're going to have H prime to the 0 is going to be equal to H prime here. We see that Q prime here is Q, big Q, Q, and then we have alpha over 1 over 2 times H bar, and then we have this as H. So now we're going to solve for H. And so we got to move this over, then solve for that, then divide by whatever. So another thing, this goes to 0. So that's important. And then move this back over. So we are going to have HS plus plus alpha 1 over 2 square root of H bar times H equal to Q. So we're going to pull out an H. So we have AS plus alpha over 2 the square root of H bar is equal to Q. now we're going to divide by that. So we have h by itself. H is equal to 1 over AS 1 over AS, yeah. Let's just keep that there. Times Q. Okay. So now we have right here. So after doing that, right, we solve for h. Then this is just h bar here. So now we know that this here is our transfer function. So this is a transfer function. And so we know that this is a first order, so first order could also be written as Ks over tau s plus 1. Right? So we are going to put this equation into the terms of this here, right? So we're going to multiply by the reciprocal of this to see where we get. So we multiply by the reciprocal, we have 2 over h bar q, and then we have q over, so now we have 2 times a over the square root of h bar divided by our alpha times our s plus, and then if we do the reciprocal of that, that's going to be 1. So after seeing this here, this is here is our k. And this here is our tau. So this can be written as Ks over tau. Oh, sorry, it's not K. It's K. So K over tau s plus 1 times Q. So this is our right answer here. So we're going to use this for the Laplace transform. Thank you. So this is part 2 of homework A. Sorry, restart. So this is part A, and this is the second question. So it says for a tank with a cross-sectional area of 2 meters square and a drainage hole, flow of 0.5 and then the square root of h meters cubed per second, where the height of the liquid level in the tank, simulate a time response of the tank with an initial steady state flow of 0.5 meters cubed per second increased to 0.55 meters cubed per second, numerically using scipy.integrate.solve IDP. Compare the numeric results against the analytical results obtained by the inverse transformation, the corresponding expression of part A1. So we're going to be using part A1's answer. So we had was h is equal to k over tau s plus 1, and then we multiplied this by q, right? So we can rewrite this as q is separated into k over tau s plus 1, and then q is a over s, and this is the magnitude of the step, right? And so we want to take the inverse Laplace transform of this here. So we can write this as h prime is equal to, we can do this as h prime is equal to ak times 1 minus e to the negative k over tau. And then we have is h, just h is going to be equal to h bar minus ak 1 minus e minus K, tau. And this is supposed to be addition. Makes sense. We want the initial height plus, which makes sense because this is the initial height and we want to add this h prime here to get the h as it is. So that makes sense, not subtracting it. And the next thing that we know is what is our graph kind of going to look like? So we have our height here, we have our time here, and we have at some height, so this is our initial steady state height, so our h bar. So it's going to be like at a steady state, so it's not changing in height. And let's say this is time is 0. It's going to jump up because we are increasing the flow rate at this, right? So it said we were going from 0.5 to 0.55. So since we're increasing this, since we're increasing the flow of the tank, it's going to increase the height of the tank. So it should kind of look like this when we coat this. So this is going to go on to the coating portion of this. So, okay. Hello, I'm Gabrielle Taylor. I'm going to be doing the coding part for homework A. So, we found the inverse Laplace transform, and now we're going to find if our exact and linear, the inverse Laplace transform is correlating and see how close it is. So let's do our coding. So the first thing we want to do is import numpy as MP, and then from scipy dot integrate, we're going to import solve IDP, and then from plotly dot subplots, we're going to import make subplots. Okay. And then, so we were given some initial functions. So our area is going to equal 2. We were given our alpha. Alpha is going to be equal to 0.5. Our Q in naught, so our initial flow rate, is going to be equal to 0.5. Our Q in is what we changed that flow rate to is going to be 0.55. We know our height naught is going to be equal to our Q in naught divided by our alpha squared. And then we know that our, okay, let's do our step function. So A is, the magnitude of each step. So that's going to be Q in minus our Q in naught. And then we have, we want to do, so now we want to do our variables for our transfer function. So K. So we know that K was 2 times MP dot square root of H naught. Of H naught divided by alpha. Right, and then our tau is equal to our K times our A. So after that, let's define our right-hand side rule. Sorry, right-hand side of our function. So this is going to be T and V as our function. So we know that H is going to equal V naught. And then we have is our dH, so this is our function that is dH, and so what we derived was our Qn minus our alpha times our MP dot square root, so square root of H naught divided by, our A. And then we're going to return, we're just going to return our DH. and this should not be that. This is going to and so then one correction to this is going to be just h, because h naught, that's at steady state. This isn't at steady state. This is the change in height, so it should change as well. So after this, let's define our graphs. So we need our t end when we do our solve IDP function. So we're going to do 500. And then let's do res equals solution of solve IDP. We're going to do our right-hand side. Then we're going to have our t end, 0 t end. Our initial guess is going to be our height naught. Our method is going to equal radu. Then our dense output is, no, wrong one. Our dense, this one there, is going to equal true. And then let's solve for our t-plot. T-plot is going to be np dot line space. It's going to be 0 to the end and 100. And then let's make our graph. So fig is going to be equal make underscore subplots. And then let's make our first graph. And this first graph is going to be our exact function. Oh, before we do that, before we do that, we're going to need to solve for our h. And our h is going to equal res dot solution of the t-plot. And, sorry, it's going to equal 0. Okay, so we wanted to solve for our h. That's our exact function. So, underscore scatter, and then we have x is equal to t-plot. Our y is going to equal our h, so that's our exact. So we're going to name this as exact. Okay, then let's add another one. So then fig dot add scatter, and then this plot is going to be our inverse Laplace transform. So what you see on the board behind me is what we already derived, and that was our h naught plus a times k, and then we have 1 minus, and then we have mp dot exponent of our t-plot divided by our tau. And then this is going to be named linearization. Linearized. Sure. So let's see what this makes. Not callable. So what was wrong with this was I had this this a here. I had it as capital A when it should have been lowercase a, because this is a stem function, not our area. And then I also didn't add that minus sign, that negative sign here as well for our tau. So this is the correct version of it. So what we can see now is here's our graph. And we can see that this is at our initial height down here, and then it shoots up pretty much, and then it kind of gets consistent when it gets farther down where the height is kind of staying similar, kind of staying at that steady state, not changing. And so this one's our exact, and this one is our linearized. And so it's very close to our exact. You can see that it's only 0.1 off of it, so it's pretty close of the inverse Laplace transform. So that is the end of homework for part A. Thank you.